Have you ever stood in a storm, truly stood there, and watched lightning tear the sky apart? That brilliant, terrifying flash of light, followed by the deep rumble of thunder that shakes you to your very core. For thousands of years, our ancestors did the same, but they didn't see a natural phenomenon. They saw gods at war, divine fury unleashed, a raw, untamable power from the heavens. They saw Zeus, Thor, Indra deities wielding lightning bolts as their weapons of choice. It was a power to be feared, to be worshipped, but never, ever to be understood. It was magic, pure and simple. This celestial fire was the ultimate expression of a force beyond human comprehension, a spectacle of creation and destruction all at once. For millennia, that's all it was, a terrifying, beautiful mystery painted across a stormy sky. Humanity was just a spectator to this cosmic drama. But while our ancestors gazed at the heavens in awe and terror, a different kind of magic, a much quieter and subtler kind, was hiding right under their noses. It wasn't in the sky, but in the earth itself. The story of our modern world doesn't begin with a thunderclap, but with a whisper. We have to travel back over 2,500 years ago to the sun-drenched shores of ancient Greece, a world of philosophers, mathematicians, and thinkers who were just beginning to ask the most profound question of all: why? They weren't content with just accepting the world as it was. They wanted to understand its hidden mechanics, its secret rules. And one of these brilliant minds, a man named Thales of Miletus, was about to stumble upon the first clue in one of history's greatest detective stories. Thales was a keen observer of the natural world. He studied geometry, predicted a solar eclipse, and believed that all things originated from water. He was a man who looked for patterns, for underlying principles. And one day, perhaps while walking along the Baltic coast where this material was commonly found, he picked up a piece of amber. Amber, fossilized tree resin, was already prized for its golden beauty, used in jewelry and ornaments. It was called electron by the Greeks. But Thales noticed something peculiar. When he rubbed the piece of amber vigorously against a piece of wool or fur, something strange happened. Suddenly, this inert, lifeless stone seemed to come alive. It began to pull small, light objects towards it, as if by an invisible hand. Bits of feather, tiny pieces of straw, dust motes, they would leap through the air and cling to the amber. Imagine witnessing this for the first time. No context, no scientific education, no one to explain what you're seeing. It must have felt like a form of sorcery. A simple stone, when rubbed, gains the power to move things without touching them. Thales documented this bizarre effect. He didn't understand it, not in the way we do. He likely attributed it to some kind of life force or soul within the amber that was awakened by the friction. But he did something crucial. He observed it, he recorded it, and he thought about it. He was the first person in recorded history to document the phenomenon we now call static electricity. That simple act of rubbing a piece of electron and watching it attract a feather was the first tiny spark of humanity's journey into the electrical age. For centuries, this remained little more than a curiosity, a neat party trick perhaps. Pliny the Elder in Rome would later write about it, noting how amber, when rubbed, could attract leaves and straw. It was a known oddity of nature, filed away with other strange phenomena like lodestones, the naturally magnetic rocks that could attract iron. People saw these things, but they didn't connect the dots. The terrifying power of a lightning bolt and the gentle pull of a rubbed piece of amber seemed to be from two entirely different universes. One was the rage of the gods, the other was a parlor game. There was no conceivable link between the cosmic and the mundane, between the fire in the sky and the strange soul in the stone. Yet, this was the first, critical step. It was humanity's first concrete realization that there were invisible forces at play in our world. It was the first hint that the universe operated on principles that were not immediately obvious to our senses. We couldn't see the force, we couldn't hear it, we could only see its effect. This simple observation planted a seed of curiosity that would lie dormant for a very, very long time. The word electricity itself would eventually be coined from that Greek word for amber. Electron, a permanent tribute to this humble, ancient discovery. It's a reminder that sometimes the most revolutionary ideas don't begin with a bang, but with a quiet observation, a moment of, that's weird. It was the beginning of a shift in thinking from pure mythology to empirical observation. The gap between these two worlds, the world of divine lightning and the world of static cling, was immense. And for nearly 2,000 years after Thales, progress was glacially slow. The mystery of the amber stone was a riddle passed down through generations of thinkers, but no one could solve it. The connection between the tiny crackling spark from a piece of amber and the immense, world-shattering power of a lightning strike remained completely hidden. It was like finding a single, strange letter from an alien alphabet. You know, it means something, but you have no language, no context, no way to decipher its true significance. Humanity held a key, but we had no idea what lock it was for, or even that there was a door to be opened. The force was always there, present in every storm, hidden in every object, waiting to be seen. And this leads us to the most profound question of all. This force, this electricity, it wasn't invented. It was discovered. It has been a fundamental part of our universe since the beginning of time. It powers the stars, it holds atoms together, it even fires the synapses in our own brains as we think these thoughts. It has always been here, all around us and within us. So if electricity was always a part of our world, why did it take humanity thousands and thousands of years to finally begin to understand and harness it? What was the missing piece of the puzzle that finally unlocked the secrets of this invisible power? Ever flipped a switch and wondered how this magic even works? We live in a world powered by an invisible force, one that we take for granted every single day. But where did it all begin? The story of electricity isn't about one single genius having a light bulb moment. Instead, it's a fascinating tale of curiosity, weird experiments, and brilliant minds building on each other's work over centuries. Let's travel back in time, long before outlets and power grids, to uncover the shocking history of electricity. Our journey starts way back in ancient Greece. Around 600 BC, the philosopher Thales of Miletus noticed something peculiar. When he rubbed a piece of amber fossilized tree resin with fur, it suddenly gained a strange new power. It could attract light objects like feathers and bits of straw. The Greek word for amber is electron, and that's where we get our modern word, electricity. For nearly 2,000 years, this was little more than a curious party trick. It was a strange phenomenon, but nobody really knew what to do with it or what it meant. Fast forward to the 1600s, during the scientific revolution. A new age of experimentation was dawning. An English physician named William Gilbert became fascinated by Thales's ancient observation. He decided to test other materials to see if they had the same power as amber. Through meticulous experiments, he discovered that many other substances, like diamonds and glass, could also be electrified through rubbing. He coined the term electricus to describe this property. Gilbert was the first to seriously study this force, separating it from magnetism, which people often confused it with. He was essentially the father of electrical studies, laying the groundwork for everyone who came after. The 17th and 18th centuries were a playground for early electrical pioneers. Imagine scientists in powdered wigs creating sparks in darkened labs. It was a very exciting time. One of the key figures was Otto von Guericke, a German scientist. In 1663, he built the first ever machine to generate static electricity. It was a large sulfur globe mounted on an axle with a handle. When he spun the globe and rubbed it with his hand, it produced a significant static charge, creating much bigger sparks than anyone had ever seen before. This machine allowed scientists to produce electricity on demand, making it much easier to study. Then came Stephen Gray in the 1720s. He made a groundbreaking discovery. Electricity could travel. He experimented with a glass tube and found that the charge could be transferred to a cork stuck in the end. He then wondered how far it could go. He started attaching various materials to the cork, like ivory balls and metal wires. In one famous experiment, he suspended a long hemp cord with silk threads and successfully sent an electric charge over hundreds of feet. This proved that some materials, which he called conductors, allowed electricity to flow, while others, like the silk threads he used as insulators, stopped it. This was a monumental leap in understanding. Now the stage was set for one of the most famous names in the history of electricity, Benjamin Franklin. By the mid-1700s, scientists knew how to generate static electricity and make it travel, but they still didn't understand its fundamental nature. Franklin was fascinated by it all, especially the powerful, terrifying form of electricity found in lightning. He hypothesized that lightning wasn't some mystical act of the gods, but was in fact the exact same thing as the tiny sparks they were creating in their labs, just on a much, much grander scale. To prove it, he proposed a daring experiment. The story we all know involves a kite, a key, and a thunderstorm. In June of 1752, Franklin allegedly flew a kite with a metal wire at the top, to attract the electrical charge from the storm clouds. The charge would travel down the wet kite string. Tied to the bottom of the string was a metal key. To insulate himself, he held a dry silk ribbon that was attached to the key. As the storm cloud passed over, he noticed the loose threads of the hemp string standing on end, indicating the presence of an electrical charge. He then brought his knuckle close to the key and a spark jumped between them. He had done it. He had proven that lightning was electricity. This experiment was incredibly dangerous, and you should never, ever try anything like it. In fact, another scientist attempting a similar experiment was tragically killed. But Franklin's success was a turning point. It demystified lightning and connected the small-scale electrical phenomena in the lab to the immense power of nature. His work also led to a practical invention, the lightning rod, which has saved countless buildings from fire. Franklin also introduced key concepts we still use today, like positive and negative charges and the principle of conservation of charge. From a piece of amber attracting feathers to Benjamin Franklin capturing lightning with a kite, this was just the beginning. The discoveries of these early pioneers ignited a revolution. Their work paved the way for giants like Volta, Faraday, and Edison, who would eventually harness this incredible force to build the modern electrified world we know today. It's a powerful reminder that every great technological leap starts with simple curiosity and the courage to ask, what if? In the late 1700s, an Italian scientist named Luigi Galvani was dissecting a frog. As his metal scalpel touched a brass hook holding the frog's leg, something incredible happened. The leg twitched, as if it were still alive. Galvani repeated the experiment again and again. Every time two different metals touched the frog's nerve, its leg would kick. He was convinced he had discovered something profound, a vital life force, an animal electricity flowing through all living things. The scientific community was electrified, so to speak. Could this be the secret spark of life itself? The idea was revolutionary, capturing the imagination of scientists and the public alike. It felt like humanity was on the verge of understanding the very essence of being. But not everyone was convinced. Another Italian scientist, a professor named Alessandro Volta, was deeply skeptical. He respected Galvani, but he believed the explanation was much simpler. Volta suspected the electricity didn't come from the frog at all. Instead, he proposed that the twitch was a chemical reaction caused by the two different metals and the moist, salty fluids in the frog's leg. The frog wasn't the source of the electricity. It was just a very sensitive detector. This sparked one of the greatest scientific debates of the era. On one side, you had Team Galvani, championing the mystical idea of animal electricity. On the other, Team Volta, arguing for a more grounded chemical explanation. It was a clash of two powerful ideas. Was electricity an innate property of life, or was it a physical phenomenon that could be created and controlled? The entire scientific world was watching, waiting to see who was right. To prove his point, Volta set out on a mission. If the electricity was caused by the metals and not the animal, he needed to create it without using any biological parts. He began experimenting with different pairs of metals. He tried zinc and copper, silver and tin, lead and silver. He noticed that some combinations produced a stronger effect than others. He even placed metal discs on his own tongue and felt a strange tingling sensation. It was an unpleasant taste, but it was proof. He was generating an electrical sensation using nothing but metals. Volta's breakthrough came when he decided to stack these metal pairs on top of each other. He took a disc of zinc and a disc of copper and separated them with a piece of cardboard or cloth soaked in salt water or a weak acid. Then he added another pair, and another, creating a tall column. He had built a stack of alternating metal discs. When he touched a wire to the top and bottom of this stack, he created something the world had never seen before. A continuous, steady flow of electricity. He called his invention the voltaic pile. It was in effect the world's first battery. Unlike the static electricity from rubbing amber or the fleeting jolt from a Leyden jar, the voltaic pile could produce a reliable current. It was controllable, dependable, and it didn't need a frog. Volta had not only proven his theory right, but he had also unintentionally given humanity a revolutionary new tool. He sent news of his discovery to the Royal Society in London, and the world was stunned. The invention of the voltaic pile changed everything. For the first time in history, electricity was no longer just a scientific curiosity, a parlor trick, or a bolt of lightning in a storm. It was a source of power that could be generated on demand. Scientists across Europe immediately started building their own voltaic piles, bigger and more powerful than the last. They used this new, steady current to conduct experiments that were previously impossible. They discovered they could use the current to split water into its basic elements, hydrogen and oxygen, a process we now call electrolysis. This opened up the entire field of electrochemistry. They found that passing a current through a thin wire could make it glow brightly, planting the first seed for what would one day become the electric light bulb. Suddenly, the possibilities seemed endless. The voltaic pile wasn't just a scientific instrument. It was a key unlocking a door to a new technological age. Ironically, in his quest to disprove animal electricity, Volta had created the very tool that would allow future scientists to study the electrical nature of the nervous system in incredible detail. So in a way, both Galvani and Volta were right. There is an electrical component to living creatures, but electricity is also a fundamental force of nature that we can harness and control. Their friendly rivalry pushed science forward, transforming a twitching frog leg into the foundation of our modern world. From this single invention, this humble pile of metal and saltwater-soaked cardboard, an entire revolution would be born. It was the moment electricity stepped out of the laboratory and began its journey into our homes, our cities, and every aspect of our lives. It was the dawn of the electric age. But the story was just beginning. Humanity now had a source of continuous electric current. The power was there, waiting to be used. But what could they build with it? What kind of world would this new power create? That question would lead to another century of brilliant inventions, fierce rivalries, and a complete transformation of human civilization. Now that we could make electricity flow, the next great challenge was figuring out what to do with it. Imagine a world cloaked in twilight, where the soft glow of gas lamps pushes back the shadows of the late 19th century. Streets are a patchwork of light and dark. Homes are filled with the flicker of open flames, and the air carries the scent of burning oil. This is a world on the very brink of a revolution, a world about to be plugged in. At the heart of this dawning electrical age stands a giant, a man whose name is synonymous with invention, Thomas Edison. Edison wasn't just an inventor. He was a titan of industry. His Pearl Street station in New York City was a marvel, a cathedral of power churning out electricity for the modern world. His system was called direct current, or DC. It was reliable, it was revolutionary, and it was lighting up the homes and businesses of the wealthiest corners of the city. Edison envisioned a DC power station on every city block, a sprawling empire of light under his complete control. But his empire had a fatal flaw, a built-in boundary. DC power was like a sprinter, powerful but short-winded. It couldn't travel much more than a mile from its source without losing significant energy. This meant that for Edison's dream to electrify the entire country, he would need thousands upon thousands of power plants, an expensive and impractical solution. The world needed a long-distance runner, not just another sprinter. Enter Nikola Tesla, a brilliant, visionary engineer who had once worked for Edison himself. Tesla was a man who saw the universe not in sparks and filaments, but in waves and frequencies. He had a different vision for electricity, one that wasn't bound by city blocks. He imagined a system that could send power soaring across mountains and rivers, reaching the most remote corners of the nation. His vision was called alternating current, or AC. Unlike DC, which flows in one steady direction, AC pulses back and forth, allowing it to be stepped up to high voltages for long-distance travel and then stepped down for safe use in homes. When Tesla presented his groundbreaking ideas to Edison, he was famously dismissed. Edison, invested heavily in his DC infrastructure, saw AC not as an evolution, but as a direct threat. Frustrated but undeterred, Tesla struck out on his own, holding the key to the future, but lacking the resources to unlock it. Tesla's genius needed a champion, and he found one in George Westinghouse. Westinghouse was a shrewd industrialist and inventor in his own right, a man who had already made his fortune with the railway air brake. He immediately grasped the immense potential of Tesla's AC system. While Edison was building a localized empire, Westinghouse saw a national grid, a web of power connecting everyone, everywhere. He saw efficiency, scalability, and of course, profit. Westinghouse bought Tesla's patents and put the full force of his company behind the AC revolution. With Tesla's brilliant mind and Westinghouse's industrial might, the stage was set for a monumental clash. This wasn't just a technical disagreement anymore, it was a war. The war of the currents had begun. a battle that would decide the very future of how we live. The battleground was everywhere, in the press, in the laboratory, and on the streets. Edison, desperate to protect his DC dynasty, launched one of the most aggressive and notorious smear campaigns in the history of technology. He was determined to paint alternating current as a deadly, uncontrollable force. The term Westinghouse was coined by his press agents as a new, gruesome synonym for electrocution. This campaign of fear reached its grim peak when New York State adopted a C for its new electric chair, a move Edison quietly supported to forever link his rival's technology with capital punishment. It was a brutal, no-holds-barred fight for the hearts and minds of the American people. But while Edison focused on fear, Tesla and Westinghouse focused on spectacle and proof. The ultimate stage for this rivalry became the 1893 Chicago World's Fair, also known as the Columbian Exposition. It was a chance to light up an entire white city and showcase one system's superiority to the world. Both Edison's General Electric and Westinghouse's companies submitted bids. The competition was fierce, but Westinghouse, armed with the efficiency of a C, dramatically underbid his rival. He won the contract. On opening night, President Grover Cleveland flipped a switch, and in an instant, nearly 250,000 incandescent light bulbs bathed the fairgrounds in a brilliant, unprecedented glow. It was a dazzling display, a city of light powered entirely by Tesla's AC generators. Visitors from around the globe stood in awe. They weren't seeing a dangerous menace. They were witnessing a beautiful, powerful, and safe future. The Chicago World's Fair was a resounding triumph for a C, proving on a massive scale that it was not only viable but spectacular. The technical and practical advantages of a C were now undeniable. The final decisive victory came with the commission to harness the immense power of Niagara Falls. This was the holy grail of electrical engineering, a project that would generate an unprecedented amount of energy. Once again, the titans clashed. The Niagara Falls Power Company had to decide which system could tame the mighty falls and deliver its power to cities like Buffalo, over 20 miles away. DC was simply not an option for that distance. The contract was awarded to Westinghouse. Using Tesla's patents, they built the first large-scale hydroelectric power plant in the world. When the switches were thrown in 1896, AC power from Niagara Falls flowed seamlessly to light up Buffalo. The war was effectively over. AC's ability to transmit power efficiently over long distances made it the clear winner and the undisputed global standard. Edison's company, General Electric, eventually had to concede and start developing its own AC equipment to stay in the game. So the War of the Currents ends with a clear victor. Alternating current. The brainchild of the visionary Nikola Tesla and championed by the industrialist George Westinghouse wins the day. The dream of a connected, electrified world is now a reality. From the grandest cities to the most isolated farms, a network of wires begins to spread, carrying this invisible force that will redefine human existence. The lights have come on, but this is just the beginning. The battle for electricity is won, but a new question emerges, one that echoes through the next century and beyond. Now that we have this power, this fire stolen from the gods, how will it truly reshape civilization? The world would never be the same. Imagine those same cities, but lit only by the flickering, gentle glow of gas lamps. Streets were dimmer, nights were deeper, and the rhythm of life was dictated by the sun. Then came a change, a revolution that would redefine darkness itself. It started with a hum, the thrum of generators spinning to life. Wires like metallic veins began to spread through the urban landscape, carrying a new kind of power. And then, the first light bulb blinked on. A simple glass orb holding back the night. It wasn't just light, it was a promise. A promise of longer days, safer streets, and a future unbound by the setting sun. The electrification of our world had begun, and with it, the dawn of modernity. This new power didn't just illuminate our homes. It began to connect them. The spark of electricity started to carry our voices. Remember the telegraph? That staccato pulse of dots and dashes clicking out messages across vast distances. It was our first attempt at a global conversation, powered by the very same force lighting our streets. Then came the telephone, a miracle of its time, carrying the warmth and intimacy of a human voice through a simple copper wire. Suddenly, the world felt smaller, more connected. Each new invention was a testament to our growing understanding of this invisible energy. We weren't just using electricity. We were learning its language. We were teaching it to speak for us, to connect us, to weave the first threads of a truly global network. Fast forward a few decades, Those early networks of wires have grown into something unimaginably complex. The gentle hum of the first power stations has become the roar of massive data centers, the new hearts of our civilization. These vast climate-controlled buildings house the digital soul of our world. Every email you send, every photo you upload, every video you stream, it all flows through these electronic cathedrals. The internet, our global web of information, is a direct descendant of those first telegraph lines. It's an ocean of data, constantly moving, constantly growing, all powered by an intricate and insatiable electrical grid. The digital revolution wasn't just about computers. It was about the electricity that gave them life, allowing us to build a second world on top of our own, a world made of pure information. And what a world it is. The pace of change has become breathtaking. Think about it. We went from simple circuits, painstakingly soldered by hand, to microchips containing billions of transistors, all in the span of a single human lifetime. That phone in your pocket possesses more computing power than the machines that guided us to the moon. We've progressed from basic calculators to supercomputers capable of simulating the universe, and now we stand on the cusp of true artificial intelligence. This exponential growth, this explosion of innovation, is all fueled by our ever-deepening mastery of electricity. We've learned to manipulate it with incredible precision, channeling its power to think, to learn, and to create in ways our ancestors could never have imagined. Each leap forward is a new verse in the song of electricity, a song we are still learning to write. Take a moment and look around you. How much of your immediate reality depends on that silent, invisible flow of electrons? The light you're reading by, the device you're watching this on, the refrigerator keeping your food fresh, the traffic lights guiding you home safely. Our reliance is absolute. It's our lifeline. Critical infrastructure, hospitals, emergency services, transportation systems, clean water supplies, all of it would grind to a halt without a constant, stable supply of power. We have woven electricity so deeply into the fabric of our society that we often forget it's even there. It's the ghost in the machine, the silent partner in every aspect of modern life. We've built a magnificent, intricate, and powerful civilization. But it's a civilization that rests entirely on a foundation of flowing charge. A foundation we must protect, because without it, our world that never sleeps would be plunged back into darkness. It's easy to feel a sense of pride, a sense of ownership over this incredible power. We built the grids, we designed the microchips, we wrote the code. We feel like masters of this domain. But maybe we have it backward. Before the first generator ever spun, before the first wire was ever laid, this power already existed. It was there in the awesome, terrifying beauty of a lightning strike, splitting the sky with 1 billion volts of raw energy. It was there in the subtle electrical signals firing in our own brains, creating our thoughts, our dreams, our very consciousness. This force has always been a fundamental part of our universe. We did not create electricity. We just finally learned how to listen to it. Thank you for watching. If this sparked your curiosity, consider subscribing for more journeys into the forces that shape our world.